Review questions for Module 6. I'll start with questions 1 and 2. 1 is asking to compare the reactants in synthesis and single displacement reactions. It's quite straightforward. We remember synthesis from Module 5, where it follows the pattern A plus B gives me AB. So in the reactant side, you just have one single reactant plus one single reactant will give us a compound in the product. And in single displacement, the general chemical equation would be A plus BC. According to the activity series, if A can knock out B, the metal, it then becomes AC and leaves B on its own. So remember, metals can only replace metals. So the difference here in the reactants, I have one single element trying to replace, if it's a metal, in this case, a metal from a compound, BC. And that single element will take the place of the metal to make a new product, AC, leaving B on its own. So let's look at some examples of those single displacement reactions in question 2. So question 2, we are going to predict the products according to the activity series of metals. And we are also going to balance the equations. If there is no reaction, you just simply write no reaction. So the first question looks at aluminum and silver nitrate. So what you need to do is ask yourself from the activity series of metals, and this can be found in your library of handouts, will aluminum replace silver, the metal, in silver nitrate? So all you need to do is find aluminum, the metal, on the activity series, and then find silver, which is down here. And so yes, aluminum is higher than silver, so aluminum will replace silver in that compound. So the new compound becomes aluminum nitrate and leaves silver on its own. Now some of you might be asking how I got the compound. So this comes from our ionic naming. You should have your polyatomic ion sheet open and your multivalent metal sheet open. So with an ionic compound, crisscross, and yes, I get aluminum nitrate plus silver. So then of course I have to balance this, which I know that there are 3 nitrates on the right, so I can actually balance this one by inspection. The aluminums are okay. There's one on each side. There are 3 silvers on each side and 3 nitrates on each side. Question B looks at zinc and lead nitrate. Zinc is in fact higher than lead on the activity series. So then from there, we just have to predict the products and balance. And I actually know that it is lead 2 nitrate because of the 2 outside of here. This would be the Roman numeral. But I'm just going to write lead as is. So yes, zinc is higher than lead. So see you later, lead 2. And it becomes zinc. And I know zinc has a 2 positive charge from my polyatomic ion sheet. Leave lead as is. And this is all balanced because I have 2 nitrates on the right, 1 and 1, zinc and lead on each side. Okay, the next question is gold and water. You actually can't see gold it's cut off on my screen. So gold is below platinum. So gold is the least reactive. So this one is straightforward because gold will not replace oh, this one's water. So gold does not react with water. If you put gold in water, it would just, like a piece of gold in water at room temperature, would just fall to the bottom of the beaker. So this does not replace hydrogen. So in this case, you say no reaction. Okay, the next question is magnesium and H2SO4. We haven't learned about acids yet. That comes later on in the course. But your book on page 166 gives you some guidance on how to write these down. So it suggests that you split up the hydrogen into hydrogen ions, because H2SO4 does form, as an acid, forms ions in solution, being aqueous. And we'll talk about this very soon. Actually, if you're doing the consolidation, you already know what aqueous is. That's ions in solution. So if I were to put this acid in water, it would form H plus ions and sulfate ions. So your book suggests that you rewrite this thing, magnesium, and maybe I'll do it under H2SO4. And I should be putting in the states. So aqueous, especially since they're given. So I know that magnesium is, yes, higher than hydrogen. Hydrogen is a special case and included here because it really depends on the activity series as to whether or not the metal will displace hydrogen in an acid form. So from lithium to lead, they do displace hydrogen from acids, and then from lithium to sodium, they displace hydrogen from just cold water, and we're going to go an example with calcium in the next question. So that your book suggests to write this as magnesium and then plus, and just count your H's, which I don't really find this easier at this point because you guys haven't learned about ions or ionic equations. We do learn that later, but I got that 2 negative from your polyatomic ion sheet. So now what it's saying is, because magnesium will displace hydrogen from acids, it actually is going to displace it and form a gas and release a gas here. So this would then rewrite as, and I'll just actually fill it in up here, see you later, H2 gas. And I know magnesium is a 2 positive being in the second group. Sulfate has a 2 negative, so it becomes magnesium sulfate, and you get H2. And we write it as a diatomic compound because it is Hofbrinkel, and states are given. This is solid, this is aqueous, this is released as gas, and so this would be your ions left in your solution as an aqueous solution. So a little different than predicting our solubility tables with double displacement reactions. Remember, this is single displacement reaction. So then the next one, as I mentioned, involves calcium and water. And as you can see in the blue arrow, it says calcium displaces hydrogen from cold water. And it actually forms calcium hydroxide and hydrogen gas. So let's just look at what your book suggests on how to write this. In this course, we're treating liquids or water as our liquid. And as I mentioned, it becomes calcium hydroxide plus H2 gas. So your book suggests to then write this as H positive and OH negative when we're writing water or when we're seeing water. So in this case, calcium is going to then join with the hydroxide here, acting as the metal because hydroxide is our non-metal, and we're losing hydrogen as gas, and then the remaining calcium hydroxide as ions in solution is written as aqueous here. So I actually do have a video to show you this.
If we add the calcium metal to water, we get a much more rapid reaction of the calcium with the water than magnesium. The reaction is very exothermic. This is due to the lower ionization energy of the calcium. We get a single displacement reaction producing hydrogen gas and the formation of slightly soluble calcium hydroxide. We can test for the hydrogen gas by collecting some of the hydrogen gas in a test tube and testing its flammability. We can test for the presence of calcium hydroxide by adding phenolphthalein indicator. The indicator turns purple, indicating that the solution is basic and that calcium hydroxide has been formed.
And we'll learn about phenolphthalein later on in the course, but as you could see, the popping sound indicated the presence of hydrogen in the test tube. So that is not quite correct. I just noticed. Because calcium, I was checking to see if it's balanced. Calcium has a 2 positive charge, hydroxide 1 negative. So if we crisscross these two, becomes CaOH2. So now all I have to do is count up my hydrogens. So remember I had mentioned if you have kind of a odd number. So I've got an odd number hydrogens here. So I am going to put a 2 in front just to start to make that 4 hydrogens and see if that makes it easier, which it does, because now I have 4 hydrogens on the right, 4 hydrogens on the left. I've got 2 oxygens, and of course I just have to have 2 in front of calcium. And then I'm done balancing that thing. And then finally, the last one, it's a similar scenario where I've got aluminum and I've got hydrochloric acid again. And again, they give us solid. I should be consistent with my states because it's given. HCl is an acid, so it forms ion in water. And then, of course, aluminum's up here and water's or hydrogen's down here. So it's very similar where it's going to become aluminum chloride and hydrogen gas as the solution in D. So then from there, I just have to balance it. So this one's a little trickier. I just guessed that eventually this chlorine was going to have to be 6 because it's our 2-3 rule, which we talked about. So I'm going to put a 6 here, which then means I can put a 2 in front of here. It gives me 6 chlorines, and then I can balance the hydrogens and the aluminums accordingly. So a few things here. You have to check your activity series of metals, and you have to know what displaces hydrogen from acids as well as from cold water. And I'm going to update the library of handouts. And you have to have your balancing rules as well as we have to know how to form ionic compounds.